So a little bio from Aaron. So Aaron received his PhD at the University of Geneva in Switzerland, where he focused on distal lead zinc skarns in southern Bulgaria. He currently writes technical content for the mining media organization Spotlight Mining and has been the executive director of Ore Deposits Hub since 2020. So a familiar face. So Aaron, take it away. Thanks.
Thanks, Michael, and thanks, Yury, and thanks to our sponsors at ODH, and thank you all for being here tonight or this morning, whatever time it is for you. It's fun for me to finally be on this side of the screen. So without further ado, I'll get on to the talk. If it clicks, there we go. So today I'll talk about the formation and geochemical footprint of distal lead zinc skarns, particularly with case study from southern Bulgaria, as Michael mentioned, where I just finished my PhD at the University of Geneva. I think it's always best to start with the acknowledgements. So I'd like to thank the sponsors who funded the project, including the SNF in Switzerland and the University of Geneva, as well as the SCG, ATH Zurich, and other collaborators. I'd like to thank my advisor, Dr. Kalin Kuzmanov, and collaborators some of whom are in this photo after a nice fun day underground, including Dr. Rositsa Vasileva, Georgi Belenkov, Simone Vezzoni, and others. And I really enjoyed my time in Geneva and this project. So why this project? Well, we're here because of mineral resources, right? So we're going to talk today about lead and zinc and why these are important. Skarn deposits can often be really high grade, maybe low tonnage, but they can be really valuable resources of metals, including lead and zinc. Lead and zinc production over time has basically started to skyrocket due to production coming from this production increase in China, which you see in the light green here, which has driven a lot of the production of these two metals in the last, say, 15 or 20 years. Right now, we mine about 13 million tons of zinc a year and 6 million tons of lead. And these are really important for different steel alloys for zinc and different battery uses for lead. And while skarns are not the primary source of lead and zinc, they do make up about 10% of all lead and zinc resources, respectively. So they are valuable and they are important. And often these high-grade skarns can be sweeteners when associated with other mineralization styles. So just to cover some of the basics, we're going to talk about what is a skarn. Skarns are rock types that are formed when fluid interacts with a host rock, which is reactive and replaces those host minerals with calcilicate minerals like pyroxene or garnet, as you see in this picture. In a classic, these skarns can form in pretty much any lithology based on the reactivity of the host, meaning that highly reactive hosts like carbonates, shown in this model from Larry Minert, will react more and therefore have a different skarn mineralogy and more extensive skarn than weakly reactive hosts such as aluminosilicates. So the fluid that forms these skarns is then transported along faults, as you can see here in this picture, or lithological contacts where it extends, laterally in this photo. And it's often generated by magmatic intrusions, although this isn't the only source. The reactivity of the different host rocks, though, is pretty evident when you look at the distribution of the distribution and size of the skarn bodies that form due to this fluid flow. Whereas in the carbonate rocks, it's more well developed, and in the aluminosilicate rocks, it's poorly developed. Because this is a reaction that occurs due to a fluid that is cooling down from its source, this always creates a zonation pattern in skarn systems. And it creates several different styles of zonation patterns that I'm going to talk about. Most of them are thermally based. So there are actually multiple zonation patterns that I want to talk about. The first links is a spatial pattern in which you have a proximal versus distal system. So if you look at this model from Silito on the right, you can see that there's a spatial relationship between the thermal and fluid source here with the proximal copper iron skarns that are adjacent to, in this case, porphyry, which is the source of temperature and fluids. Distal skarns are located here, and they are further away from the heat and fluid source, where fluid was transported along what's modeled as a fracture here. So this is the first type of zonation that I'll talk about repeatedly, and we'll focus on the distal lead zinc systems today. The second is a temporal zonation, which is prograde versus retrograde. Again, these are cooling systems. So the first skarn minerals that form, these pyroxenes and garnets that I talked about, these are often overprinted as the fluid cools and continues to flow and react with the host rock. So those minerals are destroyed, and minerals that come afterwards are called retrograde skarn minerals. This often includes the sulfide stage mineralization. The thermal zonation associated with this fluid rock interaction is also present in other ways. So if we look at this model from the groundhog deposit in New Mexico, you can actually see mineralogical zonation that's associated with this temperature. So what happened at the groundhog mine was that fluid flowed along this lithologic contact between a pluton and a reactive host lithology here. And you can see this model showing the isotherms of fluid temperatures. And you can also see that this is responsible or directly correlated with the mineralogy of the skarn system that formed there, where the highest temperature skarn formed much more garnet-rich skarn that graded out with lower temperature, with decreasing temperature, into pyroxene and then pyroxenoid skarns. Finally, if you reach a lower temperature low enough that skarn minerals cannot form, you can replace the carbonate directly in these gray blobs, which are carbonate replacement deposits, where no skarn mineral is formed. This temperature zonation pattern is associated with zonation in the major element geochemistry as well, where higher temperature skarn minerals are associated with higher contents of magnesium. Iron fits into that group and grades out into this more distal, cooler skarn, where manganese becomes the more dominant cation. In fact, other valuable metals also follow this pattern, where proximal skarn deposits are associated with iron, copper, and gold, and distal skarn deposits are often associated with lead, zinc, and silver. We'll focus on this lead, zinc, silver today, because I could talk about skarns for a long time. So I studied, my field area was in the central Rhodopes, which is this mountain range that's along the southern border of Bulgaria and the northern border of Greece. And these central Rhodopes formed due to the closure of the Vardar Ocean during the Tethyan suture zone, but most of the ore deposits actually formed after that, when the crust began to move into an extensional regime. This started about 42 million years ago, with associated with crustal melting, uplift, and extension accommodated by detachment faults. After the motion stopped along the detachment faults, extensional regime was still in effect, and you started to see subaerial volcanism and epithermal ore formation within the top couple kilometers of the Earth's surface between 31 to 29 million years ago. So we'll draw a little box around that, because that's where we're going next, in the Madan ore field, which is one of the ore fields located in the central Rhodopes. So in the Madan ore field, what you'll see here is three different tectonic units that are separated by those detachment faults, as I mentioned. You'll see several deposits in white, and then you see these red mineralized fault systems that cross-cut both metamorphic sequences and the detachment fault. This is pretty interesting because it gives us a clear timing of relationship with mineralization and the motion along the detachment fault. But it also makes pretty clear the importance of lithology when looking at these mineral deposits, as the vast majority of economic deposits are hosted in this upper lighter pink Madan unit, and that's due to the presence of marble lenses in that unit, as opposed to the darker purple. Mineralization in the Madan ore field can be simplified, lead zinc mineralization in the Madan ore field can be simplified to three types. The first are these big skarn replacement deposits, where you have massive pyroxene skarns that are mineralized with lead zinc sulfides, sphalerite, and galena. These are the biggest ore bodies in the Madan ore field, and they're the most valuable. But you can also have carbonate replacement deposits, where these veins, these mineralized feeder structures intersect the carbonate, but did not have theoretically the temperature to produce the skarn body first. And likewise, if you have this mineralized veins without the carbonate, you produce just a lead zinc silver epithermal vein. But as I'm here to talk about skarns, and I worked on my whole PhD about them, we're going to stick with the Pyroxene Skarns. It's clear that the lithological controls affect the skarn mineralogy greatly, and that fluid flow along the lithological contacts plays a big role in their generation. So along this contact, which is 3 samples from along the same contact, you can see the evolution of a prograde, basically the protolith to prograde skarn to a retrograde skarn as you move to the right. Aluminosilicates in this region can be the gneiss, pegmatites, and amphibolites, and they are all commonly seen to host epidote skarns. They have low permeability and reactivity, so those epidote skarns are pretty limited to within that lithological contact, which was the fluid flow boundary. The carbonate protolith, on the other hand, hosts these pretty massive pyroxene skarns, which is very reactive, generates a lot of secondary porosity, and allows for a lot of fluid flow, creating massive skarn bodies and lots of retrograde overprint and sulfide mineralization. If we look at the pyroxene skarns, they're almost completely composed of manganese-rich clinopyroxene called johnsonite. These form a sharp contact with the marble host, as you can see here, and they form these radial aggregates of acicular crystals that are commonly banded. These spheroids grow together, as you can see in this picture, until they amalgamate into sort of a massive skarn body that's, well, it gets quite messy. With continued fluid flow, these pyroxene crystals are overprinted by retrograde mineralogy due to the destruction of the pyroxene. So you can see here that the texture and banding of the pyroxene skarn is overprinted by the retrograde skarn minerals, which consist of rhodonite, calcite, quartz, bustamite, and different amphiboles and chlorites, which are manganese rich. Sulfide mineralization usually occurs in this stage. So if we're working on these skarn bodies, it's important then, first thing with anything you do in the field, anything you do in economic geology, almost always starts with mapping, right? So I got to go underground in 2017 and map Petrovica deposit here, which is one of 6 active mines left in the Medan ore field. They had, at the time, had just uncovered this really cool geologic relationship on this gallery. You can see in this box B, where a splay from the main mineralized structure of the Petrovica deposit actually intersected the skarn body, which you can see here in green. And so we mapped it. On the top, you can see a stitched photograph image and the sample locations for a lot of my samples here, as well as a zigzag line cut out from where this adit cuts through. And on the bottom, you can see a simplified geologic map of what we saw there. What's important to note is that on the right side of the screen, you have this mineralized vein, this mineralized feeder structure that grows into this massive, basically, this massive variably mineralized pyroxene skarn body as you move up to 20 meters down the gallery. So it's one thing to map the geology in these systems, which there's only a few lithologies. It's a lot different to map the skarn internally. And even in a massive skarn body, you do have internal skarn structures. The massive, because these pyroxene skarns form from these elongate pyroxene crystals, you can get a unidirectional growth measurement of those pyroxene crystals called a versor, which indicates that crystal's growth direction towards the open space. This means that combined, these versor measurements indicate skarn growth away from local fluids, skarn growth towards the open space and towards the fluid conduit that was occurring at the boundary between the skarn and the marble. As a whole, if we look at that plan view of that gallery isolated and the orientation of this feeder vein, we can see that measuring those skarn growth versors from this gallery basically combined to show general skarn growth direction perpendicular to that vein, which is cool because that tells us that that skarn body grew directly away from that feeder, which is what it looks like, but nobody's ever quantified that before. But these skarn versors, growth versors, also show us something different. If we go back to the geologic outcrop map and we group these versors by their growth direction and by their sector they were taken from on each skarn, they actually show us a different growth direction, and that is skarn growth directly away from the lithological context. So you can see this sample here where these growth versors are pointing down, and while skarn sectors on the bottom part of the skarn body have growth versors pointing up, and sectors from the center show both, which means that we actually have not just one growth direction away from the feeder vein, but actually another away from the lithological contact. And so the goal of this was to look at geochemical evolution as the skarn body formed physically. In terms of major element geochemistry, we learned a few things about this. So what you're seeing here is a ternary diagram of pyroxene mineral chemistry taken by electron microprobe, with magnesium in the bottom left, iron in the bottom right, and manganese content in the upper on the upper part. And in general, we see an increase in the manganese content with distance from the feeder, where the circle represents the average content of proximal or close to the feeder pyroxene. The square is intermediate, and the triangle is the furthest away. But in terms of the colors, which represent distance from the contact, it's pretty messy. I would like to note that this increase in manganese agrees with the temperature zonation proposed by the Skarn models and observations from Meinert's work, Anaudi's work, and work from Zhao Shanchang, as I said at the beginning. But that distance from the contact is going to require a lot closer look. So to identify how the geochemistry is evolving away from the contact, we have to look at the structure of each of these pyroxene skarns at the smaller scale. So cutting a thin section out shows how interesting these samples can be with elongate pyroxenes, with pyroxene crystals and growth bands of different thicknesses, textures, and crystal sizes. And remembering what we said about these growth versors, then we can say that these pyroxene crystals, each growth band was growing at a skarn front, meaning that these textural boundaries are actually ancient skarn fronts that represent that fluid pathway at different pulses of the skarn forming fluid. This is also associated with the geochemical evolution, where each band has its own distinct signature in terms of calcium, manganese, iron, and aluminum. And this becomes really important because not only are we given a relative sequence of events here, but we're also given changes in mineral chemistry. And if we look at a sample which incorporates that contact directly, even on a scale of just a few centimeters, we can see a geochemical change in the pyroxene composition with increasing distance from the contact. Each pulse of fluid that forms skarn, as you move further from the contact, shows pyroxene. So it shows an increase in the amount of aluminum incorporated into the pyroxene, and a decrease generally in the iron to manganese ratio, with more manganese being present, with a lower ratio present in the more distal, later pyroxene. This, I hypothesize then that this change in mineral chemistry, which I define as the transport parameter, acts as a sort of relative proxy for the amount of fluid-rock interaction and the distance the fluid traveled along lithological contacts before precipitating the skarn. And if we apply this relatively small hand sample measurement to the outcrop, you can see that it actually works pretty well. So here's 108 is the sample I just showed you, where this measurement was defined, and it works really nicely. But if you apply it to the average values across this skarn body, you can see that in general, more distal samples have a larger transport parameter. More proximal samples have a lower transport parameter. In terms of its trace element geochemistry, sorting my measurements by this transport parameter seems to work pretty well, in which the most distal samples, which transport parameter shows an increase in elements like lithium, rare earth elements, lead, and strontium, and a decrease in elements that might be considered more immobile, like titanium. In all, this shows us that the transport parameter, this shows us that the fluid flow along the skarn front along lithological contacts is directly responsible for the chemical evolution of these skarn bodies at the outcrop scale, meaning that during skarn growth, you have upward fluid flow along this feeder and repeated cyclic pulses of fluid reacting with this host marble. A little bit of that fluid went through the skarn directly away from the feeder, but rather most of it, and most that formed the pyroxene skarn, traveled along lithological boundaries and formed new skarn growth, propagating the skarn front along the boundary here. Basically along the skarn front. Conversely, epidote skarn remained restricted to fluid flow conduits. This creates the banding that we see in hand sample, and as we showed, this creates chemical zonation and the chemical evolution of these skarns. But how do we scale that up? This is one skarn body. How can we put that information on the district scale? Well, to scale up, we need to look at how it's possible to link distal skarn mineralization, where there's no presence of an intrusion around, to modern magmatic hydrothermal models and more proximal mineralization styles. And one way that's been done has been using epidote. We know that our epidote skarn is linked to our pyroxene skarn, and so I wanted to try it out. New models from the CODES group in Tasmania and LODE in London have shown that epidote in porphyry systems has been used to show geochemical zonation associated with the distal alteration footprints of this magmatic hydrothermal fluids associated with porphyry mineralization. And these are temperature dependent reactions, which basically make epidote unstable at the most high temperature parts of the deposit. But at medium temperatures, around 450 degrees C, which is about the same as high temperature skarn mineralization, these epidote contained anomalous trace element compositions with high titanium, zirconium, tin, among others. And as they move further and further away from the porphyry center, or the hydrothermal center, the trace element composition of the epitope contained a bunch more distal, what are called distal pathfinder elements, such as manganese, zinc, arsenic, antimony, and lead. And I wanted to see if we could apply these, the same trace element pathfinder idea to skarn systems with epidote that are not hosted in the same style of porphyry mineralization, just to see if we're in this sort of magmatic hydrothermal system. So let's look at these epidote skarns a little bit. The epidote skarns always form where the pyroxene skarns are best developed. The prograde mineralogy consists of epidote and K feldspar. These can be overprinted by chlorite calcite quartz, later sericite, adularia, and some sulfides. They, as I mentioned, these are extremely spatially limited to near fluid conduits. They're controlled by the foliation of the host rock, although it's clear that in places where there was more fluid flow and better defined pyroxene skarns, you can get massive replacement of that host rock by epidote. And it's clear, as with any skarn, that the composition of the host rock affects the mineral chemistry. So there's a major element chemical shift from more iron-rich epidote hosted in amphibolites and veins to less iron-rich epidote hosted in the gneiss and pegmatites. This means, if this is occurring in the major elements, this means that we must apply a background filter if we're going to look at the anomalous trace element composition of these rocks. And so to do that, we use the principal component analysis using some of the proximal and distal pathfinder elements proposed by Cook et al. These all covary with each other, where the distal pathfinder elements covary in the PC1 direction and the proximal pathfinder elements covary in the PC2 direction. We interpret this to mean that PC1 on the x-axis represents represents increasing distal signature, and PC2 represents in this case not proximal signature, but rather the signature of the host rock. Because these because we have applied this background filter, which we have defined as the unaltered host rock composition, meaning that if the epidote trace element composition of a given element is lower than that of the unaltered host rock, then we can not reliably use that trace element as a pathfinder. What does that look like? If we show PC1, or proximal versus distal, on the x-axis versus anomalous trace elements, so above these background lines for dependent on host lithology, then we can see that increase in PC1, or increase in this distal component, shows an increase in arsenic and antimony, which are both distal pathfinder elements in this model proposed by Cook et al. And others. Only one proximal pathfinder element exists, but it is notable that we can have up to in the tens of ppm of tin, while the other proximal pathfinders of elements are below background values. This is all great, a lot of geochemistry, it sounds neat, but how can we apply it to mineral discovery? If we put these epidote back on the map, then we can look at anomalous trace elements in epidote that might provide spatial zonation patterns. And if we look at these median values here, defined by the symbol size, we can see that the highest content of distal pathfinder elements, manganese, arsenic, and antimony, is found at the Petrovica deposit here. You can see in the bright green. And it decreases in terms of its median value as you move south. Conversely, the only anomalous proximal pathfinder element, tin, has its highest values at the southernmost deposits at Jujuska and Merzian in the south. This makes for some really interesting observations when compared with historical mining data. So if we look at the grade and tonnage of zinc that's been extracted here on the top map, or lead that's been extracted for between up until 1995, we can see that in terms of both grade and tonnage, the majority of these deposits, or the majority of the extraction at these deposits, has occurred at the Petrovica deposit, which leads me to say that the epidote trace element signature of the Madan ore field matches at least with where we've produced zinc and lead from the ore field, leading to, I hope you're ready for it, my wild hypothesis on the ore field. So looking at it now, a cross section along one of these feeder structures, with Mogilita in the northwest and Merzian in the south, this modeled detachment fault structure, we can use these proximal pathfinder elements in epidote and in pyroxene, which I didn't have a chance to talk about, but we can talk about later, to say that the southern portions, so proximal pathfinder elements, where distal pathfinder elements are most enriched near the Petrovica deposit. So, meaning that it's possible that you have increased distance between exsolving hydrothermal fluids and the Petrovica deposit than you do at the Jujuska deposit. So if you were wondering where you might find other mineralization styles or proximal mineralization styles, you would say that you would target deposits towards the south. And I'm probably way over time, so we'll just get to the conclusions. The big conclusions from this study are that massive skarns can be mapped using mineral growth versors, and these record the physical evolution of those skarn bodies, but also you can say that these also record the chemical evolution of those skarn bodies by giving you a relative age of skarn formation at different parts of that skarn. These skarns grow by cyclic fluid pulses, which result in growth banding in some skarns. But the important thing is to know that the vast majority of fluid transport then is along lithologic contacts and along the skarn front. The last thing to note is that geochemical vectoring using skarn minerals from skarn bodies dispersed over an anisotropic host lithology, such as this metamorphic terrain here, can still be used to link isolated skarn bodies to modern magmatic hydrothermal system models. And I hope to be able to do a little bit more of that in the near future. But for now, thank you for your attention. Feel free to contact me, and I look forward to questions.
Great, thank you. Thank you, Aaron. Very, very interesting talk. Lots of geochemistry, I think. So I will ask Xiaoshan Chang, who's kind of an expert in skarns. Maybe he can start off the discussion and ask a few questions. Go ahead, Xiaoshan.
Yeah. Thanks, Aaron, and for a great talk. Yeah, it's interesting. Yeah, one of the things I was looking at your aluminum content. One of the slides is showing the aluminum content of pyroxene is going higher away from the contact. Is that right?
Yeah. So
But,
aluminum content increases with increasing distance from the contact. Yes.
yeah, that's interesting because aluminum typically is has low solubilities in water, and it's difficult to transport aluminum. I was just wondering whether you have checked the host rock geochemistry, whether as different layers or different beds have more or less aluminum content. Sometimes if you have dirty limestone, then there's more clay and there's more aluminum.
That's a really good question. I think especially in these metamorphic terrains where every limestone horizon or marble horizon is not the same, but we do have good constraints on at least the bulk rock geochemistry of the marble from this gallery. In this sample that I'm showing here, that helped define this sort of transport parameter. This is all from one marble lens. It's not separated by different gneisses and the different aluminosilicate rocks. And we have constraints. The aluminum content of the marble is negligible. It's quite clean. There's a little bit of graphite in the marble, but for the most part, the aluminum content is quite low. And again, this is from a 6 centimeter difference.
Oh, yeah, that's only a small distance.
So the other interesting thing about this sample, so all my samples from this Petrovica project were from that same gallery, and you can see all the other samples in gray. So in one sample, we have both almost the maximum transport parameter and also the lowest transport parameter, just in this small range. So my thought then is that this increase of aluminum, up to almost 1% as it is, it's not so high, but my thought then is that this is probably liberated during increased fluid rock interaction, and maybe it's precipitating with the pyroxene during the dissolution precipitation of the marble, and probably neutralization of the fluid.
Yeah,
that's just my thought.
Yeah, thanks.
No, thank you.
Yeah, I have another question. Is so Epidote, I was wondering about the combination of the Epidote, but you later on you showed the Epidote, so it does have quite a bit of iron, and so Epidote and clinozoisite, and that's Epidote has more iron, that's iron 3+, so it's more oxidized condition, and so you have a oxidized condition, and you have formed Epidote in the gneiss, but why there's not much garnet around here?
For me, this is a really fun mystery of the Medan deposits, because there's actually no pro-grade garnet in the vast majority of the Medan samples. So we have seen garnet on like the absolute terminus of the Pyroxene Skarn, and we've seen tiny andradite garnets, tiny grossular garnets in the interstices that come with the sulfides in the Epidote Skarn. But there's actually only one garnet skarn body in the entire Medan ore field, and that is actually at the most southern deposit in the ore field. I believe then that the temperatures for skarn formation, the temperature of the skarn forming fluid that made these Epidote and Pyroxene Skarns, by the time it reached these deposits like Petrovica, such as here, there was just no longer the temperature required to produce the garnet.
Yeah, that's possible. Yeah, that's a good explanation. It's maybe the temperature is too low. And you mentioned that your marble has graphite.
It does have some graphite in it.
Yeah, that could also make a very good reductant when the fluid coming down to the marble and has been significantly reduced, and then the ion changed to iron 2+.
It's true because the pyroxene does contain a significant amount of iron. It's manganese rich pyroxene, certainly, but the iron that it does contain is all reduced iron. And I think it definitely has something to do with the presence of graphite. Although I will say that in some of this marble lenses, we do not have graphite and we still have this pyroxene skarn. So it may not be the only feature.
Yeah, that's very interesting. Okay, any other questions? Maybe from audience?
Yeah, thank you. There's a few questions that have come in. There's a question from Ilham. Would you like to unmute yourself?
Hi, Aaron.
Hey, Ilham. Nice.
Okay.
Thanks for joining us.
Okay. What a great presentation. Thank you. Okay. I have two questions. I'm sorry if the question are out of the topics. I'm geologist from Indonesia. The first question is, in Indonesia, Sukabumi, I found a similar character to Madan deposit, where garnet is rarely found. In your opinion, why it can happen due to the skarn zonation in general? And the second question is, I often find massive pyrite peroxide, where spatially decrease the abundance of galena and sphalerite. So in your opinion, what is the role of pyroxide in PBZN skarn deposit? Okay, thank you.
Cool, thanks Ilham. I got your message earlier today and I'm glad you joined even in the middle of the night for you from Indonesia. So as I mentioned to Zaoshan, I believe that the lack of garnet is due to a temperature, the lack of adequate temperature where the skarn formed. And I mentioned that in Madan ore field, there is, as far as I know, there is one prograde garnet skarn occurrence. And I have a picture of it. But what's interesting actually is not whether or not there's garnet at Sukabumi, but it's actually that. So we do have garnet skarns. This is one outcrop and it's the only prograde garnet skarn. For me, the rest of the garnet in Madan comes very late. You see with the sulfides. I don't want to talk about the late garnet. I mean, we can, but it's not seemingly important. But this prograde garnet skarn, the pyroxene here only exists as relict pyroxene, overprinted completely by garnet. And the sulfides here, it's really interesting, the ones you mentioned, because the sulfides here are pyrite pyrrhotite, and there's no sphalerite galena. So for me, this is going to be, again, this is going to be a more high temperature phase of the mineralization system. Yeah, for me, that's going to be the answer. So this is our high temperature example of the skarns in Madan, and maybe that can be the case too, where you, instead of using garnet as your high temperature indicator, maybe it has something to do with the pyrite pyrrhotite.
Yes. Okay.
Or another point of view, maybe the redox state.
I was thinking.
Yeah, pyrrhotite mostly occur in a more reduced environment, and
It's
that's actually
true.
That's consistent with the abundance of pyroxene, because pyroxene is relatively reduced.
That's true. I'd say in the Madan ore field, we mostly see the main sulfides in the pyroxene skarn are sphalerite and galena, which are part of this retrograde stage. And it's only this one outcrop that we found of the garnet skarn that had the pyrrhotite pyrite. There is pyrite, by the way, in the pyroxene skarn, but it's mostly that's subordinate to the sphalerite galena. The pyrrhotite in the pyroxene skarn is pretty minimal when you talk about like modal percent, which is strange to me because the redox, it's almost like we have competing redox states in these two different skarns, because the garnet should be theoretically an oxidized mineral, and the pyrrhotite that it's coming with is clearly not.
Yeah, we have another question from Azam Sultani. Azam, would you like to unmute yourself?
Yes. Hi, Aaron. How are you? So your trace element signature is very interesting because I work almost on the same suit for VMS deposits. So the question mark here is for tin. Okay.
Mhm.
So do you think that, for example, imagine if you had chloride along with your epidote here, then what would happen? All of your thing gonna go to epidote or chloride. So I'm just wondering, is it a mineral specific characteristic or something else?
Thanks, Azam. It's nice to see you again and talk to you. And yeah, it's a good question about tin and what's controlling this district scale trace element zonation, why there's tin, for example, in some of the epidote, but not all of the epidote. If I think about it in the way of like David Cook's model that I talked about at the beginning, those proximal trace elements are no longer, they're only available in the higher temperature solutions due to the way they complex. So I think that basically what I'm trying to show is that there's a thermal pattern in the Madan ore field, not that there's a change in the trace element abundance. So like theoretically, I would say that deeper in the ground or closer to the source, you would find more epidote with these higher tin contents. And again, high tin in these is around 10 to 20 for the most part. There's one sample with 80 ppm tin. I think the only, as far as I've found, the only other prograde mineral that wasn't part of the protolith assemblage in the Epidote Skarns was K feldspar. So
Okay.
I did not analyze the K feldspar for its tin content.
Okay, that was my guess. Possibly there is something else as well. Okay, so that is K feldspar in your system. Okay, pretty cool. Thank you.
No, thank you. Thanks for the question.
I have sort of a question with suggestions. You have an epidote that is a good mineral, I think, for doing the stable isotopes for hydrogen and oxygen. And you could use oxygen isotopes of different minerals to constrain the temperature if you would like. And also you mentioned that there's a graphite, but you can actually use it as the temperature, well, thermometer for doing the Raman CM thermometry, carbonaceous material thermometry. If the temperatures, say below 650, then this thermometer really kicks in, and this is something that can help you in resolving thermal changes through your deposit. So you mentioned multiple times that temperature is one of the key elements here for you to rely on, but there are a couple tools that I think worth noting for the future to use.
Yeah, that's a really good point. I think more stable isotope work on this would be pretty useful. I think right now there's a few studies on stable isotopes. I did some stable isotopes in my study, but mostly in the calcite. I was working on this Skarn front boundary layer calcite and the fluid processes happening there. I think looking at mineral pairs, so in the Pyroxene Skarn we're limited because it's mostly just pyroxene in that phase. But in the Epidote Skarn, there could be potential for this, particularly where we see the K feldspar and epidote intergrowing. The problem is in the Epidote Skarn, a lot of the crystals are quite small. And I don't know about developing a in situ standard for these two minerals.
How abundant the graphite is?
It's like in the 1% range, depending on the different parts of the marble. Mostly less, but I guess it can get that high. Their marble flakes, the graphite flakes in the marble are basically define the foliation in the marble. So the marble is all conformable with the surrounding gneisses, and the orientation of the graphite flakes actually matches that of the gneiss foliation. Interestingly, something to say about Zhaoshan's point is that these graphite flakes are actually found in the skarn as well. They are not completely oxidized out of the system. They are found trapped in the skarn system as well.
In terms of graphite, probably one thing to consider is the timing. And the graphite probably formed during the metamorphism. You have those gneiss, and they are probably earlier than the hydrothermal system.
That's a good point, Zhaoshan. I have isolated 2 samples of graphite, and then the calcite that goes with it. These will have carbon isotope measurements done on them. I presume that we'll find the metamorphic temperature from this, not necessarily the metasomatic skarn formation temperature. But we'll wait till the data comes in, right?
And do you know the age of the deposit?
Ooh, I have constraints on the age. So effectively we tried to look at calcite dating for this deposit, but the calcite was too low in uranium to do anything. We tried dating some of those garnets. The age results were less than stellar, so they didn't help resolve anything. But our best estimates is that mineralization was ended by 29.9 million years, and this is from sericite that precipitated on top of sulfides, so like as a hydrothermal sediment. And then I found, me and my advisor and our team found a place where the skarn was actually growing adjacent, or basically at the contact with the rhyolite dike. So we took a sample of the rhyolite dike, which was skarnified, and dated that. And that gives us an upper age constraint at 31.2. So we have it down to about 1.5 million years. But that's a good question. And it's been actually one of the main questions in the Madan ore field is, are these skarns associated with metamorphism, or are they associated with the dikes that are present in the region?
I work on the Caijiaying skarn in China. It's the same thing. It's hosted in mid-proterozoic gneiss graphite amphibolite with marble lenses, and then dike came in. Some of them are 200 million years, some of them are 140, and yeah, the age, there's at the beginning always debate about the timing, whether it's sometimes because the marble lenses is folded during the metamorphism, and then the replacement of skarn obviously also now has a folding form because it's selectively replacing the marble lenses, and then that's became the debate. You see, oh, the skarns are in the folding form. It must have been deformed, and so that comes the debate whether it's early together seen metamorphism or pre-metamorphism got folded, or it was a later, much younger, and selective replacement. Probably similar to your situation here.
Yeah, we're in a situation where most of the skarns here are not like the skarns aren't deformed, and the marbles are mostly, everything's more or less gently dipping. But that's pretty interesting, because then you actually get back into looking at the internal texture of the skarn minerals again, because if it's deformed, it should say that, you know, that skarn growth was pre-metamorphic. Do you know, is it Niels Janssen in Sweden is working on these metamorphosed lead zinc skarns. And it's pretty interesting what they're, trying to identify a metamorphosed skarn is it's tricky. I think it's cool.
It is tricky. Yeah. Because those ones, the skarns are hard, unless you have chloride, garnet pyroxene, they are pretty hard. And if you have deformation, they're like insurance, they break and they don't deform. Hard layer, soft layer, hard layer, soft layer is always the soft layer deforms and the hard layer breaks. Rheology contest. I see there's another question, so maybe.
Yeah, Aaron, there's another question from Lavi.
Okay.
Who's asking about the graphite. So did you find graphite in the marble? Could you explain how there's graphite in the marble? And is graphite a mineral from the prograde or retrograde metamorphic condition?
Cool. Thanks for the question. I find many of the marble lenses in the Madan ore field contain graphite, and I believe that this is graphite that formed due to organic matter that was metamorphosed during the mountain building event, which predated all of the mineralization. So I have graphite for me as one of the protolith in the protolith mineral assemblage, rather than in the prograde. It's not in the skarn forming mineral assemblage. I might have some slides, or at least sorry for all the animations, y'all. Yeah, so here's like a little cartoon mock-up where I show that the graphite is actually existing in these little things in the marble, and in most cases it barely even changes orientation when it gets basically overgrown by the pyroxene skarn. In some cases, you could even argue that it's inert during skarn formation.
Okay, thank you. We have a question from Nico. Would Nico like to unmute himself?
What a great presentation. My name is Nico. I come from Indonesia. I want to ask you some advice for our exploration team now work in.
Okay. I'm not familiar with the deposits at Kalimantan, but I would say that the first step for me is mapping, which I'm sure that you're already doing well at. All of my mapping was underground, meaning that I was mapping individual skarn bodies. Working at a single deposit, I think it would be very important to map and document any mineral zonation you see in these skarn bodies, and then map those skarn bodies relative to each other. Because what you'll see is that the proportion of pyroxene to garnet can actually be used as a zonation factor, which is something I've learned from Zhaoshan and Larry Minor, but you can use this percentage of garnet in your system to say like that's mapping towards more proximal mineralization styles. If, like in Madan, you have no garnet, then you might need to look at geochemistry. And you can do this with whole rock, but I think one of the things that I've shown, and a lot of people have shown in skarn systems, is that whole rock geochemistry in skarns can be a bit misleading because they can be a little bit messy. And it's better to do, in my opinion, it's better to do mineral chemistry. So then you use chemical zonation as your mapping technique for exploration.
I just want to make another comment is that Aaron is looking for jobs, and if you have a good job, tell Aaron and he can help you a lot and work together with you. It's even better than just a very broad and very general comment. Yeah.
Absolutely. If somebody has a skarn they want to come talk about, send me an email. I'd be happy to look at or work on different skarn systems. Or yeah, I am looking for jobs, looking to get back in the field and see some new rocks, learn about some new systems.
Right, a little shout out for Aaron Hantsche.
Woo, thanks.
Awesome. Thank you very much, Aaron. And I think there's no more questions. So thanks a lot for a great talk. And thanks, Ashan, for joining and being and starting off the discussion with us. Thank you, everybody, for joining, and see you soon.